Welcome to the tutorial of computational suite for bioinformaticians and biologists. In this video today, I'm going to take you through different functionalities of CSPB and how you can put with different inputs into different modules and what all results and visualizations we can achieve from these modules. So before I do that, let me introduce myself. So myself, Praneeth, and currently I'm working as a senior bioinformatician for Cincinnati Children's. Um, so the whole idea behind developing CSPB was to basically empower researchers from both wet and dry lab to perform downstream bioinformatics analysis with little or no bioinformatics experience. Currently, CSBB is this our Shiny app is packed with 6 modules, which is visualization, normalization, basic stats, differential expression, correlation profiles, and function and path enrichment. And I'll take you through each and every module and how we can input files into these modules and what are the different functionalities or changes that you can do to achieve different results. So before I do that, let me give you a walkaway on how the app functions and what are the different things that you can play with. So on the left-hand side, you see that there is a box for which names module. And from here, you can choose whatever module of interest. For example, let's say you want to do a normalization, so you can choose normalization. And then accordingly, there would be other inputs that would be required for the app to function. For example, in normalization, it requires an expression file to be uploaded. You have to choose a normalization method and then choose a visualization method. And then going to the tabs here on the right. So the About tab basically gives you a little bit of information about what CSBB is and what all modules it currently holds. CSB Shiny has a GitHub page, which I would like you to visit and definitely post issues, suggestions, improvements on the GitHub section. Then there's also a command line application of CSB, which you can use to process your next generation sequencing datasets like ATAC-seq, ChIP-seq, RNA-seq, and all these functionalities that we have in the Shiny is also present in the command line version. And if you want to deploy the Shiny app on your own servers, the code is freely available and you're welcome to do so. If you're using CSBB Shiny in your research, please cite the GitHub page. The next window that you have is result window, which basically will show all the results that are being processed by the modules. Then we have the visualization window where you can see what plots are being generated. And at last, we have the getting started window. So this window basically gives you a little bit of introduction of each module and their functionalities. And it also gives you access to the sample files, which you can basically click and get all the sample files to get started with testing the app and seeing how it performs on different data sets. And then you can start putting your own data accordingly. So what we'll do is basically we'll start with normalization for now. So let's say I go here and I select normalization, and then I will go and browse expression file from my data set. So if I go to this folder and then I choose a file which is data file, and I upload it here. So once you upload it, you have to choose a normalization method. Now Shiny, the CSBB provides you with multiple options here. The first is upper quantile. And upper quantile, basically what it does is it uses the between lane normalization concept, where the 75th quantile of each sample is used to scale. And that's how the upper quantile normalization works. And it tries to basically scales your all samples to the 75th quantile of the samples. And then we have median, where it uses the median to do the normalization. Full is basically using the 100th quantile. Log2 is generally a log2 transformation of the data. And z-score is where basically for each gene, it takes out the mean and the standard deviation across samples, and then use the mean to subtract from all the expression values, and then divide those subtracted expression values divided by the standard deviation. And that gives you a z-score value for each gene across the sample. Then you have a way to visualize your data. You can use PCA, which is principal component analysis, t-SNE, which is stochastic neighbor embedding, and then heat map. So PCA is a linear dimension reduction approach, whereas t-SNE is a non-linear dimension reduction approach. So for now, we'll select PCA as the visualization method and upper quantile is the normalization method. So once we click on the result window, you'll see that you'll have a file, which is kind of a data frame here, and you'll have all the upper quantile normalized values. And as you go to the visualization window, you can see a PCA plot will be generated here, right? Right here, you can see the PCA plot, and then you can see what is the variance values covered by PC1 and PC2, and that says that on PC1, 28% of the genes are contributing to the variance, and PC2, 14% of the genes are contributing to the variance. Now, this is a dummy data, so this has, I think, 150 genes and 45 samples. You should put your own data and see how the genes or how samples are clustering based on based on the variance covered by the genes. Now, as you go to result window, you can download this data by clicking download results, and this should basically help download the whole upper quantile normalized matrix into a file on your desktop. Then if we go to change the normalization method to, let's say, log2, so then you can see your values are now log2 transform, and as you go to the visualization window, your PCA will change accordingly. Now, let me give you a little bit introduction of how t-SNE works here. So let's say you want to look at a t-SNE of your samples. So one file that is required by t-SNE here is a group file, where you have to basically set each sample in your data to a group. And you can find that sample file on the sample files folder on the GitHub. But for now, let me upload a group file from my desktop. And once I do that, what happens is it will generate a t-SNE plot for the samples. Now you can definitely play with the perplexity here. So perplexity value basically helps you find out more contrast between the samples, the group of samples. And as you increase, the samples will move further away, or basically see if there are more reductions that can be done on the t-SNE1 and t-SNE2. And let me change the value to 8. So you can see the clusters move a little bit here and there, but in general, I can clearly say that group 2 and group 3 look more similar when on basis of the expression when compared to group 1. Moving on, so let me put a z-score matrix here, and as you put a z-score normalization, the t-SNE plot changes a bit, but overall conclusion will still remain the same, and that should be the effect from the normalization. It should not basically change your results a lot from one method to the other. The other thing is that we can do here is basically look at a heat map. So for example, I'm sticking to z-score, but I say no, instead of t-SNE, let's do a heat map. So I select heat map from here and go to visualization window. So it will generate a heat map for you. And then it has several options on clustering, rows and columns. So by default, it's set to rows and columns to perform clustering on, and perform scaling on is default set to row. But sometimes you just want to have a supervised clustering. Let's say you just want to cluster the genes. So you can set it to rows, and that way the heat map will change and will only cluster the genes instead of the columns. And for performing scaling, so scaling is basically just rescaling your expression values for each gene from -6 to 6 or -3 to 3, whatever scaling it chooses by default. I generally prefer to scale because that basically brings out more contrast between the samples on your heat map. Now, moving on to the visualization. So once you select visualization and you go back to the result window, let's say I just want to choose that file again. And as I do that, the file is uploaded. Now here in the result window, it's doing nothing on no operations is being done on the file. It's just showing the data as it is, because it's just this module is just for visualization purposes. But as you go to the visualization window, you'll see that there is a heat map which is generated from the data inputted. And then you can go back, change, and you'll see the t-SNE or PCA as selected. Now, definitely normalization would affect and should make the overall PCA plot or t-SNE plot a little bit better, because it should remove certain variances in the data or effects in the data which comes from sequencing, or let's say there are batch effects and stuff. So, but I would definitely recommend using more appropriate approaches for batch effect removal, like COMBAT or SVA. But in case of normalization, upper quantile and the log transformation definitely help to assume a normal distribution and make it a more easy to cluster on the PCA and t-SNE. Going to the next, we have basic stats. Now, once you go to basic stats, there is no visualization window for that. So there's no relation that we do for basic stats. But what basic stats is important for is basically it gives you mean expression, median, median standard deviation, standard deviation, variance, min, max, and sum of your genes expression across samples. And this could be very useful when you, let's say you have control and disease environment and you just subset your matrices for control and treatment, and you want to quickly see which genes are highly expressed in your control and compared to treatment, and without doing any differential expression for that sake. So yeah, in this way, it could be more useful. And it's a simple module, but sometimes it could be really helpful, as I said, for differential expression, or in general, just looking at the trends of your expression of genes across the sample. Now, let's go to the differential expression. So differential expression is a module which would be very useful for a lot of people out there who want to perform differential expression on control versus treatment kind of data set, or let's say disease versus wild type, something like that. So in differential expression, we need a count file to upload. So what I'll do is I'll go ahead and upload a count file here. And as you do that, basically what will happen, the select control samples is basically you can have to select here, select your control samples or treatment samples from here. So I'll go ahead and select all the control samples here. And for treatment, I'll go and select all the treatment samples. And once you do that, what will happen is it will start processing and create, basically generate a differential expression table for you. So, and then you have certain filters that you apply on these tables. For example, by default, it's set to 0.5 log2 fold change, which basically translates to 1.5 fold change. And then you have a false discovery rate of 0.2, which is basically saying that, let's say you have 100 genes, so 20% of these genes could be false positives. But generally, I would recommend using a 0.05 cutoff. That basically means 5% FTR, and a log fold change of 0.5 should be fine for now. Now, once you do that, you see that now your gene list is basically you have 2,162 genes which are differentially expressed. The other cool factor that I like here is basically you can search for a gene of interest and see what log fold change, CPM, and the p-value and FTR that gene carries. So let's say I want to search for IL-6. So as you type IL-6, it'll pop up and you'll see that, oh, it's differentially expressed. It's upregulated in the treatment, and it has a very stringent FTR. So similarly, you can search for other genes which you like. Then, once you have these differentially expressed genes, the question comes, what all kind of visualization you can directly do in CSV with these DE genes? So there are multiple visualization methods that you can do here or use here, basically. So by default, it's set to heat map. So you can definitely go to the visualization window and see a heat map of all the differentially expressed genes. And it's clearly showing that there's a differential expression between two groups, which is control and treatment. And there are like 2,162 genes here on the rows. Again, you'll have the same functionalities of performing clustering on rows, columns, or both rows and column, and then scaling on row or column, or none of them. Then if I go ahead and let's say assume or make this change to 1 log2 fold change. So what would happen is basically, this is basically saying that now the log2 fold should, the fold change is now equal to 2. So now you see that the number of genes should have reduced, and automatically the heat map will also change. So if I go to the result window, you can see that now there are only 545 entries present for these cutoffs. Similarly, for other visualization methods are PCA. Now, if you again go to the visualization window, it will use the genes, the differentially expressed genes, to basically perform a principal component analysis on your samples. Similarly, you can choose for t-SNE, heat map, or the other two, which is function and pathway enrichment and volcano plots. Now, volcano plots is something which is very useful when you're doing this analysis and quickly want to show your collaborators or your or just find out what are the differentially expressed genes and what are the significant ones. So this is really helpful in doing that. It basically takes your DE genes, uses the log fold change in p-value, and creates a scatter plot which will show the significance versus log fold change. And you can clearly see that there are these genes in red which are highly significant or differentially expressed. Now, apart from volcano plot, you can quickly also do function and pathway enrichment, which could be again very useful, because let's say you have 500 differentially expressed genes and you want to see what are the pathways or functions enriched in these for these genes. you can just click on that button and you can quickly see all the functional and pathway enrichment in your data. So definitely you have a lot of immune system regulation here going on. You have cytokine, you have interferon, you have antiviral mechanism, and then again, a lot of interferon signaling which is connected. Now here you can clearly see that the p-value, adjusted p-value is being used here for making this plot. And all these interactions or the network that you're seeing is highly significant. And the dot size basically represents the number of gene sets that are available for these pathways, enriched pathways or functions. Now, moving on, let's go to the other module, which is correlation profiles. Now, correlation profiles can be very useful and is really helpful in doing certain analysis. For example, let's say you have an expression matrix where you have 20,000 genes and you have, let's say, 50 samples. Now, you want to find out how your samples are correlated. And this could be helpful in also finding out if there are batch effects between your replicate set, between your samples when you have done it on different batches, the batch effect in your replicates, or there is any sequencing effects across your samples, or in general, just finding out how your sample, like control set versus treatment set, differs, or any other conditions that you're interested in. Now, let me choose a file which has like 78 samples and it's a TPM matrix. So as I do that, what will happen, it will load the file and you can select, by default it says that you can do correlation among samples, and then you can select a correlation method here. So what I'll do is, I'll show you how the result matrix look. So once you do that, it will show you all your samples and then how they are correlated based on the expression values. And the best way to visualize it is basically a heat map. So once you go here, it will show you how your samples are correlated. Now, I can clearly see that these samples here, which are SARS-CoV-2 or lung, they are definitely very different from all the rest of all the other samples when compared to themselves. So this is a very good way to see that these are samples which are completely different set from the rest of the other, and it would be more important to look at them and what genes are basically expressed in those samples, which basically distinguishes them from the other. And let's say you want to now perform a correlation on your genes, and there's a gene set that you want to use for correlation. So what you can do is you can select genes from here, and then you can upload a gene list, which is, in this case, I'm using a default D gene list which I have from dataset. And once I do that, this result window will be updated. And now you will see all these genes that you inputted and how their correlation ranks among all the other genes in the matrix. So basically, and how this would be useful again is basically, let's say if I go to IL-6, for example. So if IL-6 is present, it will quickly show you how it's correlated to all the other genes that you have inputted. And this could be useful in quickly finding out the co-expressors and like positively regulated or anti-regulated genes. Then the other way to basically look at the data is basically go again to the visualization window. And now this would be updated and it should show you the correlation among the genes. Now, it's very clear that a lot of gene sets here are anti-correlated with all the other genes, but definitely there is a set of genes which are positively correlated in these blocks which you see. Now, there are different methods of correlation that you can use from, like Pearson, Kendall, or Spearman. So let's say if I want to do a Kendall correlation. So the heat map will be updated, as you can see here. And similarly for Spearman, it will again be calculated with the Spearman correlation values. Now, Pearson is more of a linear correlation method, and Spearman is a rank-based correlation method. So in terms of TPM and counts matrix, I would prefer using a Spearman correlation rather than Pearson. Then going forward, we can use functional and pathway enrichment. Now, sometimes as you can see that it's saying you can choose species twice. It's just a lag in the system. So what I'll do is just refresh the system quickly, and then go ahead and choose the function and pathway enrichment. And then let's say I again choose the same DE genes that we have here. And once you do that, and you go to the result window, so what we'll do is basically calculate all the pathways and functions that are enriched in the data. So it takes a little bit of time to generate this matrix because it has basically it queries a huge amount of database, that whole reactome pathway to come up with these functions which are enriched or pathways which are enriched. So as you can see, again, all the immune signaling pathways are quite enriched with these PE genes. And it basically gives you the description of what they are, gene ratio, then give you p-value, adjusted p-value, and all genes which were found in your data set and were enriched in this for this pathway. And as you go to the visualization window, again, it will take a second to basically come up with the visualization. Should we have, yep. Okay, so again, you can see a network here, which basically is comprised of all the networks and pathways and functions which these genes are enriched for. And again, the color basically shows here how your p-value is significant, how significant is the p-value, and then the size or the dot of size basically show how many genes are enriched for these pathways. So again, you can see a lot of influence signaling, immune signaling, and cytokine signaling activated here. So going back, so this was a quick tutorial highlighting different features of CSPV and how you can use them. And if you have any questions, issues, suggestions that you want to make, please use the GitHub's issues section and post your queries there. And I would be happy to get back to you as soon as possible. And this is something I'm developing over time. And there are a lot of different functions or modules that will be coming soon to CSPP, like doing annotations for ChIP-seq data, ATAC-seq data, and even some modules for single cell. So yeah, keep me posted through your issues, suggestions, feedback, and I'll be happy to help. Thank you. Thank you for your time.